We'll have ample time to talk about this on Monday. In the meantime, today I guess we'll finish chapter 3, and I guess get ready for the exam. Do you have any questions? Okay, so last time we talked about, we started talking about section 7, right? L'Hopital's rule, and I actually wrote L'Hopital's rule for one particular form. So I figured the way I'm going to approach things right now is the following. We have something called indeterminate forms. And we've seen a bunch of them up to now throughout the semester. And today, as the day is going to progress, we're going to learn how to deal with all of these types of indeterminate forms. So one of the indeterminate forms was 0 over 0 or infinity over infinity, right? And these were the two ones that I talked about last time, right? I'll leave some space there to actually write more of them, but what I was going to say here is the following. If the limit as x goes to a of f of x divided by g of x is equal to, and I'm going to write equal with quotation marks. This is basically a short version of L'Hopital's rule, what I'm basically trying to say. If it's 0 over 0 or infinity over infinity, then the limit as x goes to a of f of x divided by g of x is just going to equal the limit as x goes to a of f prime of x over g prime of x. Right? This is what we talked about last time. And I looked at, I guess I got a chance to look at like one problem, right? I don't know if I did more than one. I don't remember. I don't think I did, right? So anyway, other types of indefinite forms, and I'm going to come back to them really soon. But other types of indeterminate forms would be 0 times infinity, infinity minus infinity, 0 to the 0 power, infinity to the 0 power, or 1 to the infinity. Okay? Is this making sense? Why are they indeterminate forms? Because you don't really know who's going to win, right? If I have, think about it, 0 over 0, infinity over infinity. If the 0 in the denominator wins on 0 over 0, then you end up with infinity. If the 0 on the top wins, you end up with 0. If they end up actually going to infinity or going to whatever number is at the same rate, then you end up with an actual number. Same goes for infinity over infinity. Why is 0 times infinity indeterminate? Well, again, we don't know which one actually gets faster there. Is the 0 stronger than the infinity, or the infinity stronger than 0? Okay? Here, we talked about this in the past, right? The point is I have infinity minus infinity, so technically, what could I possibly get? Well, I could get any variety of answers. I could get 0, I could get an actual number, or I could get infinity, right? The best case scenario, think about x squared minus x. Take the limit as x goes to infinity, right? Technically it's infinity minus infinity, but I'm hoping everybody knows by now that polynomials are characterized by the largest power. So technically x squared is the one that's going to win, so you're going to end up with infinity, right? Is that making sense? 0 to the 0, why is this undetermined? Well, because 0 to any power is 0, right? But any number to the 0 power is 1, right? So which one of these actually is going on? Is it 0 or is it 1? Or is it something else? Okay? Similarly with infinity to the 0 power, right? Infinity to any power is going to be infinity, but any number to the 0 power is 1. So do you see how these kind of end up happening? Yeah? Okay. So we'll come back to those later on throughout the section. So I figured for the beginning part, let's look at these 0 over 0, infinity over infinity cases and see what we're dealing with. So simple case. How about if I look at Problem 1 on page 193 says the limit as x goes to negative 1 of x squared minus 1 divided by x plus 1. Bless you. So, in this instance, if you actually put in minus 1 for x, which is what we started doing, right? The whole point is, when you look at limits, is you put in the value for x and you see what situation you're in. So if I put in minus 1 for x, I end up with 0 over 0, right? Now this was actually a problem very similar to your test problem, which pretty much everybody got right. The point was, it's a rational function, so if the fact that it's 0 over 0 means I can factor out an x plus 1, both in the numerator and the denominator, and cancel them out, right? That's how we learned how to deal with them in the past, right? Well, how about we actually do it differently? How? Well, it's 0 over 0, so notice that it's 0 over 0, which means I can apply L'Hopital's rule. So it'll give me the limit as x goes to minus 1 of 2x over 1. Put in minus 1, you end up with negative 2. Does that make sense?
Why'd you get a lot harder?
Of course they will get a lot harder. For example, number 3. And I wouldn't say that it's a lot harder, but the limit as x goes to pi over 2 plus of cosine of x divided by 1 minus sine of x. So, I cautioned you about limits in general when we looked at limits in chapter 2, and I'm going to say a couple of words about this here as well. We have this powerful tool now called L'Hopital's rule, which says, I'll just take derivatives and keep working, right? However, that only works if you're in a 0 over 0 or infinity over infinity case. So the first thing you want to do is you want to plug in whatever value is to see if you're in a 0 over 0 or infinity over infinity case. Does that make sense? Is everybody understanding this? So, as it turns out in this case, that is the case, because cosine of pi over 2 is 0. Sine of pi over 2 is 1, so we're going to be in a 0 over 0 case. Is that making sense? That's why I actually try to keep always writing what situation we're in. That way, it basically shows that we verified, we know we're in a case in which we can apply L'Hopital's rule, and we can proceed on. Okay? So, applying L'Hopital's rule gives me the limit as x goes to pi over 2 plus of negative sine x divided by negative cosine x, which ends up being, okay, the limit as x goes to pi over 2 plus of tangent of x, which is, keep in mind, tangent of pi over 2 does not exist. However, pi over 2 is a vertical asymptote. So the limit as x goes to pi over 2 plus is negative infinity, you say? You don't seem convinced. So since you don't seem convinced, a picture is worth 1,000 words, or so they say. Here is pi over 2. Pi over 2 plus means I'm on the right side of the vertical asymptote, and my tangent is at minus infinity. Everybody sees that? Yes? Wonderful. Okay, now notice, by the way, this is a situation, and it's kind of nice the way the problems are lined up. Notice in problem 1, it was a 0 over 0 where we end up with an actual number, right? Here we again had 0 over 0, but the actual answer at the end was minus infinity, right? If I would have taken this plus out, if I would have started this without the plus, then the answer would have been does not exist, right? Does that make sense? So notice how a variety of answers you can accomplish by, even though they're all starting at 0 over 0. Okay? Number 5. The limit as t goes to 0 of e to the t minus 1 divided by t cubed. So what do? Put in 0, we notice it's 0 over 0. So applying L'Hopital's rule gives us e to the t over 3t squared, which is 1 over 0. So what can we say? Plus infinity, we say? Why plus infinity? It's 1 over 0, but this is a 0 squared, which means it's always positive. Right? Okay, picture's worth 1,000 words. Yet again. This is the graph of y equals 1 over x squared. Right? Notice that at 0, both sides should at infinity, which makes my limit be infinity. If this would have been just 1 over x, then one of the branches actually goes to minus infinity, so they go in opposite directions, so then we can't actually say that it exists. Is this making sense? Okay. I mean, assuming you care. Okay, number 7. The limit as x goes to 0 of tangent of px divided by tangent of qx.
Are P and Q constants?
P and Q are constants, yes. I guess to make things nice, we could have just used 2x and 3x or something like that. So what now? Tangent of 0 is 0. So we're in this lovely situation of 0 over 0. And so applying L'Hopital's rule gives us what?
Secant squared.
Secant squared of what?
P of x.
Secant squared of p of x times p divided by secant squared of q of x times q. Right? Again, 2 words. Last word is rule. First one is chain. Right? So what now? Is it now? What's secant of 0? Secant is 1 over cosine. What is cosine of 0? 1. So secant of 0 is 1. So this is just p over q. Is this making sense? This is what I said. Don't just assume that it is 0 over 0 or that you just have to take derivatives. Plug in at every given step, plug in whatever you have and see what situation you're in. Is that making sense? Yes.
What would it be p squared over q squared?
Why would it be p squared?
Because we still have the p and the q inside of something. So when we have secant squared of px, wouldn't that be 1p?
When you put in 0 for x, you end up with secant squared of
P under all.
Keep in mind, constants do not come out. This is the argument of secant. You can't take the p out. So once we actually said that its secant of 0 is 1, that means we take into account the entire argument of secant. Okay. 9. The limit as x goes to 0 plus of ln of x over x. I'm waiting.
Negative infinity or 0, right?
Exactly. See the into the. This is why I said the first thing you want to do, you want to see what situation you're in, and not all of a sudden jump to actually take derivatives. So what is this actually ended up being? Well, it's ln of x, which is ln of 0 plus is minus infinity divided by 0, right? What is minus infinity divided by 0? Minus infinity divided by 0. Let me write it that way. Right? How about if I write it as the limit as x goes to 0 plus of 1 over x times ln of x. Now, as x goes to 0 plus, where does 1 over x go? It goes to 1 over 0 plus, which is positive infinity. So this is positive infinity times minus infinity. So the end result is minus infinity. Does this make any sense? Yes.
Where do you get the ln of x?
ln of 0 plus? Think about the graph. ln of 0 plus is minus infinity. Yes.
Okay, so to get the 1 over x, kind of get copy dot flip, only there was no fraction. Right?
I'm not sure I understand.
Oh, never mind.
X over 2 is the same thing as 1/2 times x. Right? That's just properties of fractions. But what I'm trying to get to here, and this is why I like this particular problem, is, again, the only reason why you would apply L'Hopital's rule if you're in the case of 0 over 0 or infinity over infinity. If you have 0 over infinity or infinity over 0, notice that in reality you have either infinity times infinity or 0 times 0. Do you understand that? Yeah? Okay. Let's see. How about 11? The limit as x goes to 0 of 5 to the t minus 3 to the t divided by t. So since you all look very excited to be here today, why don't you solve this and tell me what it is? First of all, what situation we're in? 0 over 0? It's 1 minus 1?
Oh yeah, you're right.
Right? So since it's 0 over 0, what can we do? Take derivatives? Okay. The answer will surprise you. Oh, I'm sorry. It's supposed to be t. Obviously, if x equals 0, that's just very boring. So, are we finding an answer? The answer is ln of 5 minus ln of 3. Anybody got that? We got 2 yeses and a lot of disinterested looks, and so maybe I should give you a pop quiz. Then you better get working. What is the derivative of a to the x? A to the x times ln of a. So what happens when you take the derivative of the numerator? What do you get? 5 to the t times ln of 5 minus 3 to the t times ln of 3 divided by 1. And then what happens when you put 0 in for t? Right? So we're in a situation of 0 over 0. We apply L'Hopital's rule, and we end up with the limit as t goes to 0 of 5 to the t ln of 5 minus 3 to the t ln of 3 divided by 1. Right? So now, if you put in 0 for t, 5 to the 0 is 1. 3 to the 0 is 1, so you end up with ln of 5 minus ln of 3, also known as ln of 5/3, if so you choose to write it. Is this making sense? Okay, how about 13? The limit as x goes to 0 of e to the x minus 1 minus x divided by x squared. So, again, you have fun with this and tell me what you get. I'll give you a hint, the answer is 1/2. Don't know if that actually helps. And I'll give you another hint. Once you apply L'Hopital's rule once, you'll end up actually having to apply it again. Everybody got it? Yeah? Yes? So, 1/2? Do I need to solve it? Okay. So, again, we're in a situation of 0 over 0. So what's the derivative of e to the x minus 1 minus x? It's just going to be e to the x minus 1, right? Divided by 2x. Put in 0 in for x again, and you're again in a situation of 0 over 0. So we have the limit as x goes to 0 of e to the x over 2. And now if you put in 0 for x, you end up with e to the 0, which is 1, divided by 2. Is that making sense? Okay. How about 15? The limit as x goes to infinity of x divided by the natural logarithm of 1 plus 2 times e to the x. And again, the answer might surprise you. The limit is 1. So what situation are we in? Infinity over infinity, right? Okay, so we're in infinity over infinity, so we can apply L'Hopital's rule, right? Remember, 0 over 0 or infinity over infinity, you can take derivatives, right? So what do we get? One over one over 1 plus 2e to the x times 2e to the x, right? Okay, now one of the things about L'Hopital's rule that we're going to notice as we're going to do more and more of these problems is that in general, chances are once you apply it once, before you can do anything else to it, you need to actually simplify it or rewrite it, because in this fashion it doesn't really look like much, right? I don't really know what to do with this anymore, right? So notice that this is the same thing as the limit as x goes to infinity of 1 plus 2e to the x divided by 2e to the x. Is everybody seeing this? So now what happens when we put infinity in for x? Infinity over infinity, right? So what to do? Do it again? Alright, so what happens when you do it again?
I guess we're stuck in infinity.
What happened? So 2e to the x over 2e to the x is just 1, right? So it's just the limit as x goes to infinity of 1, which equals 1. Yes? A over b, all divided by c over d, is a over b times d over c. Right? This is just 2e to the x over 1 plus 2e to the x, which means the denominator, this denominator ends up being in the numerator, right? Make sense? Okay, how about 17? Since you're having so much fun. The limit as x goes to 1 of 1 minus x plus ln of x divided by 1 plus cosine of pi x. So, first step, ln of 1 is equal to 0. Yes. So what do we get when we put in 1 for x in the numerator? 0. Ln of 1 is 0. And what do you get on the bottom? Cosine of pi is? Cosine of pi is? Cosine of pi is? Negative 1. 1 minus 1 is 0. We end up with 0 over 0. Right? So what happens if we have 0 over 0? Well, then we apply L'Hopital's rule. What do we get on the top? Negative 1 plus 1 over x divided by negative sine of pi x times pi. As it turns out, the pi doesn't actually play any role. So what next? Zero over 0, right? So what next?
Do it again.
Do it again? Okay. What do we get on top? Negative 1 over x squared. Very good. What do we get on the bottom? Negative cosine of pi x times pi squared. Yes? Pi is just a number, right? Or something you eat in the morning. So when you take the derivative, this pi doesn't play a role, right? So what is the derivative of minus sine pi of pi x? It's going to be minus cosine of pi x times pi. Times this pi makes it times pi squared. Right? So now, what happens when you put in 1 for x? I'm sure nobody really expected this particular answer for this particular problem. One over pi squared. Yes? It should be negative, yes, thank you. Yes?
Oh, why is it negative? Like, should it be negative over negative?
What's cosine of pi? It is not 0, it is not 1, but it is?
Oh, negative.
Yeah? Is this making sense?
Yeah.
So we end up with minus 1 divided by minus 1 times pi of x. Multiply all of them out and you end up with minus 1 over pi squared. Right? Which is obviously not what you expected when you looked at the original fraction. Right? Okay. Okay, how about one last one? 19. And by one last one, I mean one last one before we get to other indeterminate forms. X to the 8th power minus a times x plus a minus 1 divided by x minus 1 quantity squared. So now, since there's no trigonometric functions in here, I'm confident you can do it. Keep in mind a is a constant. Why do we know a is a constant? The limit is in terms of x, right? So anything not labeled x is a constant, right? So I guess first question would be, what happens when you put in 1 for x? 0 in the numerator, 0 in the denominator, we end up with 0 over 0, right? Yes? Okay? So now what happens when you take derivatives?
1 minus.
Sorry. There's this little knob over here. Oh yeah, I should have waited for another week and do this for Halloween, right? Okay. So what now? 1 over 0?
It is 1 minus.
Are you sure? What is the derivative of the numerator?
1
A times x to the a minus 1 minus a, and everything else is 0. Right? So when you put in 1 for x, you get a times 1 minus a, which is 0. You don't seem convinced. So what is the derivative of the numerator? A x to the a minus 1 minus a divided by 2 times x minus 1. Right? Make sense? Put in 1 for x, you end up with a minus a on the top, which is 0, divided by 0. Right? So we apply it again. So now what is the derivative of a times x to the a minus 1? A times a minus 1 times x to the a minus 2 divided by 2. And so your limit is a times a minus 1 over 2.
I got lost the a times a minus 1.
What's the derivative of x times a to the a, or a times x to the a minus 1?
Bring the a minus 1 down.
Okay.
And subtract another 1. Okay.
Of course, this is assuming, they haven't written anything here, but this is assuming a is not equal to 1. Right, because if a would be equal to 1, then you can't actually do that. Right? Is that making sense? Do you understand why a can't equal 1? Because you would have, at this step, you'd have x to the 0, which is 1. So when you take the derivative, you wouldn't have x to the minus 1. But anyway, that's, yes? Well, what happens when you put in 1 for x? You end up with 1 to some power, right? 1 to any number is 1. And so, right? Is that making sense?
Boy, how did we get the final answer? What, did we simplify it?
You put in 1 for x.
Oh.
That's what we've been doing all along. What's missing from this step to this step? The limit is. Since the limit... Since the limit is 1, since the limit doesn't appear here anymore, that means we actually evaluated it, right? Okay. Do we have enough of them? We did all of them, so there's not that, and I can't really do your even ones because I can't really, take away from your joy. I mean, look how ugly it's outside. What are you going to do outside anyway? Singing in the rain? Limit as x goes to 0 plus of the square root of x times ln of x. What do you get? Since I said that was the last one, what would you expect to get now? 0 times infinity. That was the next type of indeterminate form we were looking at, right? Put in 0, you get 0, the square root of 0 is 0. ln of 0 plus is minus infinity, so this is just 0 times infinity, right? Is that making sense? How would we handle something like this? We can't take the derivative because we don't have it as 0 over 0 or infinity over infinity. However, let's make a lovely box over here. 0 times infinity can be written as 1 over infinity times infinity, or 0 times infinity can be written as 0 times 1 over 0. So we can either write it as infinity times over infinity, or we can write it as 0 over 0. Do you understand that? 1 over infinity is 0, right? So if we look at the previous problem, whenever you have 0 times infinity, the key idea is one of your two functions should be written in the denominator. Okay? Everybody understands this? Why? Because if we do that, we're going to end up with infinity over infinity or 0 over 0. The function that you never want to write in the denominator is ln. And I'll show you in a second why. So technically, I can write this as the limit as x goes to 0 plus of the natural logarithm of x divided by 1 over the square root of x. Or I can write it as the limit as x goes to 0 plus of the square root of x divided by 1 over ln of x. Is this making sense? Why? Look in this situation. The numerator is minus infinity. Denominator is 1 over 0, which is infinity. Right? So I have infinity over infinity. Right? This is going to be a situation in which I'm looking at infinity over infinity. This is a situation in which I'm looking at 0 over 0. Do you understand that? Yes? Okay. So technically we could do either or. Which one should we do? Top one, why not the bottom one? I said you should never put ln in the denominator, right? Why did I say that? Well, let's look at the bottom one and take the derivative and see what we end up with.
0 over 0.
It's clearly 0 over 0, right? Because that's what we said we're going to have. But what's the derivative of square root of x? 1 over 2 times the square root of x, right? What's the derivative of 1 over ln of x? What you're telling me that is that the derivative is minus 1 over ln of x quantity squared times 1 over x? It's a fraction. It's 1 over ln. So when you take the derivative, you have to apply the quotient rule. Or the simplified quotient rule, if the derivative of 1 over g is just minus 1 over g squared times g prime, which is exactly what I have here. Notice, I started off with 1 over ln of x. I ended up with something much more uglier. Hence, it's not nice to put ln in the denominator. Everybody sees that? So let's attempt the other one. So the limit as x goes to 0 plus of the square root of x times ln of x equals the limit as x goes to 0 plus of ln of x divided by 1 over the square root of x. We're in the situation of infinity over infinity. So the numerator is 1 over x. The denominator is
1 over x squared times.
Yeah, that would probably be easier.
right?
No idea what she said.
1 over the square root of x is x to minus 1/2. Taking the derivative is just minus 1/2 x to minus 3/2.
Oh.
Right? So what now? This is another one of those instances in which I kept telling you throughout the semester, learn to write with positive exponents, because what is 0 to minus 3/2? As it turns out, it's not 0. However, let's write it with positive exponents. We have the limit as x goes to 0 plus of 1 over x divided by minus 1 over 2 times x to 3/2, right? Which is the same thing as minus the limit as x goes to 0 plus, I just took the minus out, of 2x to 3/2 over x. Which is the same thing as minus the limit as x goes to 0 plus of 2x to 1/2, which is the same thing as minus the limit as x goes to 0 plus of 2 times the square root of x, which equals 0.
Alright.
Yes.
Alright, step 1, you get to 2x to power 3 or 3x top.
Here?
Yeah, so that's the top.
Okay. A over b divided by c over d. It's a over b times d over c. So the denominator becomes the big denominator. The denominator here becomes the numerator.
Why did I put a negative sign? Oh.
Everybody sees this? Yeah? Okay. Well, since you're all having fun with this, let's continue on. 23. The limit as x goes to 0 of cotangent of 2x times sine of 6x. This should be a good one. So of course, the way to approach this is assuming you know trigonometric functions, plug in 0 for x. So what is sine of 0?
0.
That's 0. What's cotangent of 0? Which is infinity, right? So this is a situation of 0 times infinity, right? Again, remember, 0 times infinity is indeterminate. It could be 0, it could be infinity, it could be some fixed number. As it turns out, we're in luck, this one will be a fixed number. What number would that be? That'll be interesting. So this is a situation of 0 times infinity. How would we handle this? Again, we need to get it to 0 over 0 or infinity over infinity, right? True, or Should we do that? Sure, why not? So this is the same thing as sine of 6x over tangent of 2x. Right?
What?
Cotangent is 1 over tangent.
Oh, okay, 1 over tangent. And then you have 1 over tangent. Right.
What? Cotangent is 1 over tangent. All I did is just wrote cotangent as 1 over tangent.
Oh. So you just rewrote it.
That's the game plan. It's 0 times infinity. We want to get it to 0 times 0, or infinity times 0 over 0, or infinity over infinity. What situation are we in? 0 over 0. Since for 0 over 0, we can apply L'Hopital's rule. What do we get on the top? Cosine of 6x times 6. What do we get on the bottom? Secant squared of 2x times 2. What happens when you put in 0? Cosine of 0 is 1. Secant squared of 0 is? Secant is 1 over cosine, and so it is 1. So it'll just be 6 over 2. I don't know if you remember this or not. We actually dealt with a very similar problem to like this when we looked at limits. The fact that the limit as x goes to 0 of sine of x over x is equal to 1. We wrote it in terms of sines and cosines. And by we I mean I remember I solved the problem. And I separated it into 3 limits. And he had sine over x, and then x over sine. And then we had the cosine separately. I know, it's been like a month and a half ago. Okay, 25. The limit as x goes to infinity of x cubed times e to minus x squared. So what are we looking at? 0 times infinity, right? Yes? So one of them needs to be moved into the denominator. Which one should we move? The e2 minus infinity is 0. Right? Think about the graph. It just goes.
So why is e to the 0?
It's not e to the 0. X is minus infinity. So it's e to the minus infinity. So which one should we move? Yes?
I would say the e to the negative x squared, since that's already in the denominator technically.
The key idea is when you have exponential functions, you should move those in the denominator. Why? Because it's much simpler to take the derivative of x cubed over e to the x squared as it is to take the derivative of e to the minus x squared divided by 1 over x cubed. Is everybody seeing this? Yeah? Okay. So that means that this is 0 times infinity, so I have the limit as x goes to infinity of x cubed over e to the x squared. Now I'm in a case of infinity over infinity. I can apply L'Hopital's rule, and what do I get? Three x squared divided by e to the x squared times 2x. So what now? we get infinity over infinity, right? But remember what I told you in general L'Hopital's rule. You would like to simplify things before moving forward. Notice that I can cancel 1x with 1x. So I will be left with the limit as x goes to infinity of 3x over e to the x squared. Oh, sorry, 2 e to the x squared, yes. And now when you put infinity in for x, you get infinity over infinity. So we apply it again. So we end up with the limit, as x goes to infinity, of 3 over 4x e to the x squared. Which is just 0. Right? Is this making sense?
Boy. Okay, so we have 4x e to the power of x squared. Well, the first thing we did is we brought the 2 down to the x. Now we have e to the power of 2x. We brought that 2x down to 2.
What is the derivative of e to the x squared? E to the x squared times 2x. Okay, and I had another 2. You said the derivative of e to the x squared is e to the x squared times 2x. Times 2 makes 4x. Okay? Well, since you're also versatile in this, let's try something else. The limit as x goes to infinity of x e to the 1 over x minus x. So now, what would this limit be? Well, you have to be careful. Put in infinity for x. You get infinity times e to 1 over infinity, which is 0. E to the 0 is 1. So I end up with infinity minus infinity. Right? Is that making sense? So now how do we approach this particular type of an indeterminate form? The key idea is, again, can we actually write it as infinity over infinity or 0 over 0? Now, in order to get there, whenever you deal with infinity minus infinity, the first step is to write it as 0 times infinity. That's usually the first step in trying to get to that. So notice here, what happens if I factor an x? I have x times 1 times e to the minus x times e to 1 over x minus 1. Right? What happens when I put in infinity now? I have infinity times 0. Right? Everybody sees this? So now I'm in the previous case. By now I should be you should all be very versed in this. What do? One of the terms need to be moved in the denominator, right? Which one should we move? Normally, you would say the one with exponent, not in this case. Why? Well, if I move this in the denominator, I will have the denominator will be 1 over this mess. When you take the derivative, it'll just get a lot uglier, right? So we're going to have the limit as x goes to infinity of e to the 1 over x minus 1 divided by 1 over x. Does that make sense? We're in the 0 over 0 case. Apply L'Hopital's rule. What do we get on the top? E to the 1 over x times minus 1 over x squared. And the denominator is just minus 1 over x squared. See how nice? Yes.
How come when we do this, we don't do the portion?
Because that's not what the theorem says.
I think if we're taking a derivative of a fraction.
But you're not taking a derivative of a fraction. Yes? Okay. Notice how the fractions cancel out. E to the 1 over infinity is e to the 0, and the whole thing becomes 1. Remember what I cautioned you about any of these indeterminate forms. You could get anything from 0 to any number to infinity, right? And you have no idea which one it is. Which, by the way, needless to say, when you're going to have this on the test, I would expect you to actually explain to me how you got to the answer and not just guesstimate. Because, 0 or infinity are usually the two most popular choices, and you might be lucky enough to actually hit on one of them. Is this making sense? Okay. So since we're having so much fun, I guess we only have 10 minutes. So why don't we move to the last type of indefinite forms. So 31 says the limit as x goes to 0 plus of x to the x squared. It's 0 to the 0 power, right? And remember what I told you about 0 to the 0 power. It's indeterminate, right? Everybody remembers why it's indeterminate? 0, 1, or it actually turns out it could be anything else in between, right? As, again, with all of these, it could be anything else in between. So how do we handle this? Well, we haven't talked about any of these problems. But do you remember, if you look at this particular function right here, do you remember how to take the derivative of this? Logarithmic differentiation was the only way you could actually take the derivative of, right? Well, that's, yes?
Is that kind of like simplifying equation?
Yes, the whole point is to try and make it simpler so you can actually tackle it. So that's exactly what we're going to do here. Technically, you can't take the derivative, you can't apply ln both sides because we don't actually have an equation, right? Logarithmic differentiation said y equals x to the x squared, apply ln both sides and move on, right? But we don't actually have an equation, we just have an expression, right? So what can we do? Well, what we can do is we can say this is equal to the limit of e to the natural logarithm of x to the x squared. Is this making sense? E to the ln disappears, right? They're inverses of each other, and you pick back x to the x squared, right? Now, e is strictly increasing, continuous, and all that fun stuff, which means what I can do is I can say this is the same thing as e to the limit as x goes to 0 plus of the natural logarithm of x to x squared.
Use one of those things to get move outside.
Yes, again, because it's continuous, it's differentiable, it's got all the nice properties, you can actually interchange the limit and the function. So now we take separately the limit as x goes to 0 plus of natural logarithm of x to x squared. So first thing, we can figure out what? Why did we apply e to the ln, or why did we look at logarithms? So we can take the power down, right? Nothing, we're just taking the limit separately. I just don't necessarily want to write e to the limit at all times. So I'll just take the limit first, and then as a last resort I'll just plug it in back to the e. So we'll come back to that. Is this making sense? What do we do next? Has to be in a particular form to take derivatives. This is a situation in which we're looking at 0 times infinity.
Oh yeah, butterfly.
So this is 0 times infinity, which means we need to move 1 in the denominator. Which one should we move? X squared. Very good. So we have ln of x divided by x to the minus 2. I just wrote it as x to the minus 2 so you can see it a little simpler. Instead of 1 over x squared. When we take the derivative, that's why I figured I'll help you out. So now we're in a situation in which we're going to have infinity over infinity. So it's the limit as x goes to 0 plus of 1 over x divided by minus 2x to minus 3. So it's the limit as x goes to 0 plus of minus 1/2 times x cubed over x. I'll pause for a second to see if you see where I'm getting everything.
Okay.
Yes.
Alright, so 0 plus the power of negative 2 is infinity.
Yes, it will be infinity because of the negative. X to minus 2 is just 1 over x squared. 1 over 0 is infinity. Remember, we had x squared times ln of x. By moving x squared in the denominator, it automatically makes it to be infinity. So far, so good? Yes? Think about this. 1 over x, x moves in the denominator, right? I have x to the negative 3. If I want to make it positive 3, I move it in the numerator. So I'll have x cubed over x. So now that just becomes the limit as x goes to 0 plus of minus 1/2 times x squared. Okay, which becomes 0, right? So what is our answer? E to the 0, which is equal to 1. Yes?
Okay, I'm a little lost on how you move negative 2x to the power of negative 3 to the power.
Well, I just explained it.
Yeah, I know.
What happens when you move x? What happens if you want to write x to minus 3 to a positive power?
Change it to x to the positive.
Okay, on the numerator.
But the negative 2 doesn't go with.
That's a constant. It's not an exponent.
Okay, okay.
Okay, let's see. It's 33 on 193 says the limit as x goes to 0 of 1 minus 2x to the power of 1 over x. No, actually 1 to infinity is another indeterminate form. That was the last one I wrote.
That was a comment.
As it turns out, this particular function will equal 1 over e squared. Okay. We can play with this more if you want, and I'll show you how to apply e to the ln's and all that fun stuff. But I figured at this particular juncture in time, let me show you a trick. Remember, the limit as x goes to 0 of 1 plus x to the 1 over x is equal to e. Remember that? So, the limit as x goes to 0 of 1 minus 2x to the 1 over x is equal to the limit as x goes to 0 of 1 plus the quantity minus 2x to the power 1 over minus 2x times negative 2. This particular limit is e. So this becomes e to minus 2. If you don't believe me, do the e to the ln, take, move the fraction out, take derivatives, and you'll see what you end up with. Is this making sense? Yes? Do you understand why this is the case? The key idea is x has to match that x, right? When x goes to 0, clearly minus 2x will go to 0, right? So 1 plus a quantity that goes to 0, I have to make sure I raise that to the power of 1 over that quantity. So that's where that's coming from. But my original equation was 1 over x, so I have to make sure I come back to 1 over x. So minus 2 and minus 2 has to cancel. And so I'm left with that. Yes?
Okay, so for all 1 to the power of infinity problems on homework,
Sorry?
for all 1 to the power of infinity problems like this on homework, should we be able to do this?
If you think you can, I guess. But you don't have to. E to the ln works for every single one of them. So the method we employed for the previous problem will work for every single one of these. Okay? So you don't have to be creative if you can't see it. Like for instance, one of your problem in the homework is 1 plus a over x raised to the power of bx. Would you know how to do it in this fashion? So if you don't, then just apply e to the ln and it should come out.